In this video, we're going to take a look at absolute value functions. Now, we already have seen the base absolute value function f of x is equal to the absolute value of x. We're going to develop a couple of tools that we need to deal with other absolute value functions. So we're going to investigate some of the features of the absolute value function, and then we'll look at other functions that involve absolute values as well. The first feature of the absolute value function is the operation of the absolute value. The absolute value of x does one of two things. If you plug in a non-negative number into the absolute value, then you're going to get that number back. However, if you plug in a negative number into the absolute value, then you're going to get the opposite of that number. In other words, when you plug in a number into the absolute value and take the absolute value of that number, you get a positive, or non-negative, I should say, output. So if I plug in a positive 5, I get out a positive 5. If I plugged in a negative 7, I'd get out a positive 7. The opposite of negative 7 would be a positive 7. So depending on what you plug in, you're always going to get a positive. Now, that poses an interesting feature of the absolute value operation. If I said the absolute value of x is equal to 5, there's actually two numbers that I could have plugged in for x to give me a 5. I could have plugged in a 5, or I could have plugged in a negative 5 into the absolute value and then gotten out a positive 5. And that's the one thing that we're going to use most often in this section, that feature. We're going to start out this section solving some absolute value equations. Whenever we have an equation with an absolute value in it, what we can do is isolate the absolute value on one side of the equation and then have that equal to hopefully a real number. Now, if this real number b on the right-hand side of this equation is negative, we know the absolute value of any number is non-negative. So if b is non-negative, then this absolute value equation has no solution. On the other hand, if b is positive or equal to 0, let's just say positive. If b is positive, then there's going to be two solutions. We could say that a could have been equal to positive b, or a could have been equal to the opposite of b. This gives us two equations to solve, and therefore we can solve each individually. Let's do an example for solving a couple of absolute value equations. The first equation says absolute value of the quantity x minus 2 minus 7 is equal to 10. We start out by isolating this absolute value of x minus 2. In order to do that, we would add 7 to both sides. When I add 7 to both sides, I get that the absolute value of x minus 2 is equal to 17. Now, the thing inside the absolute value could, to make this equation true, the thing inside here could be positive 17, or the thing inside here could be equal to negative 17. So that's how I set up my two equations. I say x minus 2 is equal to 17, or x minus 2 is equal to negative 17. Either way gives me a solution. For each of these equations, I solve individually. So I would add 2 to both sides. The first equation would give me x is equal to 19. The second equation would give me x is equal to negative 15. If I wanted to check my answers, I could plug in 19 into my original equation, see that it gives me a true statement, and then also plug in negative 15 into that first equation and see that it gives me a true statement. Both of these work. I won't go through the process of plugging them in and checking, but both of them do work. So this absolute value equation has two solutions. Let's take a look at this example. Here we have 3 times the absolute value of quantity x plus 1 minus 14 is equal to 2. I start out wanting to isolate that absolute value. In this case, I would add 14 to both sides. When I add 14 to both sides, I get 3 times the absolute value of quantity x plus 1 is equal to 16. Then I divide both sides by 3. That gives me the absolute value of the quantity x plus 1 is equal to 16 over 3. You could write that in a lot of different ways. I'm writing it as an improper fraction. Now what we can say is that the thing inside the absolute value could have been 16 over 3, or the thing inside the absolute value could have been negative 16 over 3 to make this equation true. That leads me to have two equations, one which says x plus 1 is equal to positive 16 over 3, and the other which says x plus 1 is equal to negative 16 over 3. In order to solve both of these, I would subtract 1 from each side. When I do that in the first equation, x would be 13 over 3. In the second equation, I'd get x is equal to negative 19 over 3. Again, that's what I get by taking negative 16 over 3 minus 1. Again, you could write these as mixed numbers. You could write these as decimals rounded to a couple of decimal places. But for right now, I'm going to leave my answer as improper fractions. So that's how we solve absolute value equations. Let's do another couple of examples. Let's solve these two absolute value equations. And if you want to try these on your own, push pause on the video and go ahead and try them on your own. In a couple of seconds, I'll show you how each is done. So in this first equation, we already have the absolute value isolated on one side of the equation. We have absolute value of 0.2x plus 4.5, and then equaling 7.2 on the other side of the equation. So that means the thing inside the absolute value, 0.2x plus 4.5 can either be a positive 7.2, or that thing could be 0.2x plus 4.5 could be equal to a negative 7.2. Now I have to solve each of these. I would subtract 4.5 from each side in each case. When I do that to the first one, I get 2.7. In other words, 0.2x is equal to 2.7. And on the other side, if I take negative 7.2 minus a 4.5, I get negative 11.7. So 0.2x is equal to negative 11.7. Now I simply just divide each number by 0.2. 2.7 divided by 0.2 is 13.5. So that first equation becomes x is equal to 13.5. The second equation becomes x is equal to negative 58.5. So that's the solutions to this equation, this absolute value equation. I should say these are the two solutions to this absolute value equation. In this other equation, what I would do is I would start by subtracting 10 from each side. I'd have 2 times the absolute value of x minus 1 is set equal to negative 6. When I subtract 10 from both sides, that's what I get. And then I would go ahead and divide by 2. So we get absolute value of x minus 1 is equal to negative 3. I have basically solved this and isolated for the absolute value. And now I'm ready to give my solution. I don't have to separate in this case because notice that the number on the right-hand side of the equation is a negative. In other words, we're getting something that is telling us that there's a positive number which is equal to negative 3. That obviously is always false. I should say non-negative rather than positive. So maybe I'll say that. Something that's non-negative. So that means positive or 0. Equaling negative 3, that's obviously false. And so what this means is that this absolute value equation has no solution. There's nothing you can plug in for x in order to solve this. Now, I do want to point out that most of the time we get 2 solutions or we get the no solution. There is one weird case where it's equal to 0 that we would get a single solution. I'm not going over that. Also, in these instances, I've always put the absolute value around an expression with the variable. So that's what I'm meaning by absolute value equations. Absolute value is around an expression with a variable. There are more complicated absolute value equations that we'll get to, and we might see a couple later on in a different section, but these are the types that we focus on in this section. Those types being that we have a single variable inside our absolute value. And then there's no other variables anywhere else. Now it's a short jump from absolute value equations to absolute value inequalities. So let's say instead of having an equal sign, we had a less than sign, or a greater than sign, or a less than or equal to, or a greater than or equal to. If we're solving absolute value inequalities, I'm going to do them in a very similar way to solving absolute value equations. I'm going to isolate the absolute value on one side, and then I'm going to examine the inequality. If it never works, then there's going to be no solution. If it always works, it's all real solutions. But if it sometimes works, then we're going to create two inequalities and solve each, just like we created two equations. Now, with inequalities, the thing we have to worry about is that when we multiply or divide both sides by a negative number, then the sign flips. We go from a greater than to a less than, or vice versa. We go from a greater than or equal to a less than or equal to, or vice versa. That's whenever we multiply both sides by a negative. And when we create an inequality, when we create one of the inequalities and we use the negative, then that's in effect multiplying or dividing both sides by a negative. Let's do an example. Let's solve the following two inequalities. We have absolute value of x minus 2 is greater than or equal to 10, and the absolute value of x plus 1 minus 14 is less than 2. So in order to solve this algebraically, this first one, we've already have the absolute value isolated on the left-hand side. So we can create two different equations. Now, one of them is going to be our standard x minus 2, and then we're going to keep the sign facing the same way when we use the positive 10. Or on the other side, when we do x minus 2 and compare it to negative 10, we actually have to flip the sign because that is like multiplying by a negative on both sides. I know that's hard to maybe fathom, but remember what the absolute values operation said to do. If the thing inside our absolute value is a negative number, then we take the negative of that. The opposite of that would be greater than or equal to 10. And so multiplying both sides by a negative, we'd get the standard x minus 2 is less than or equal to negative 10. In other words, this equation comes from the fact that really the opposite of x minus 2 is greater than or equal to 10. Multiplying both sides by a negative would flip that sign, and that's where we get this example. If the thing inside is positive, then I just keep it this way, and that's where we get this side. If the thing inside is negative, then we need to do that, and that's where I get this. So basically, when you use the negative number, we flip the sign. Now we can add 2 to both sides, giving us two different inequalities. X is greater than or equal to 12, or X is less than or equal to negative 8. This gives me two inequalities that are going to interact with each other. Now, the way they interact can be shown on a number line. So that's what I'm going to do. I'm going to draw a number line. 12 is somewhere over here, over on the right. And then -8 is over here to the left of that. Okay. What these two inequalities are saying is that x could be any number bigger than 12, and that would give me a true statement. By the way, it could also be equal to 12, so technically when I draw a circle around 12, I should fill it in on the number line. And then I'm going to shade to the right. Similarly, with -8, x can be less than or equal to -8. So I'd fill in a circle on the number line. At -8, and then point my arrow to the left. So on a number line, this is what the solution would look like right there. If we did this in interval notation, we do parentheses, -infinity. Then we do comma, -8. Then we do a square bracket. So -8, -infinity up to -8 takes care of this section. And then we'd start back up at 12 all the way to positive infinity. The way to do that is to use a union sign, union, square bracket, 12, comma, positive infinity, parentheses. So that would be my interval notation for this inequality solution. Anywhere from -8 infinity up to -8, and then from 12 to positive infinity. Notice that having two numbers on the number line kind of splits my number line into three distinct regions. And with this example, the way these inequalities work and go together, we have two regions where solutions can come from. One region over here on the left side, one region over here on the right side. Now let's look at the next question. The next question has the absolute value of x plus 1 minus 14 is less than 2. I would do a similar thing, but this time I have to isolate my absolute value. We get absolute value of x plus 1 is less than 16 when we add 14 to both sides. Then I can separate into two different inequalities. The one where I use positive 16, I keep the sign facing the same direction. The one where I use -16, I have to flip the sign into the opposite direction. So my two inequalities that I get are x plus 1 less than 16 and x plus 1 greater than -16. Solving each of these just takes a subtraction of 1 on either side. If I do that, on the left-hand side, I get x is less than 15. My right-hand equation says x is greater than -17. Now I have to think about how these two interact on the number line. So once again, if I have a number line, we have two numbers that are of interest to us, the negative 17 and the 15. Now, the way these interact is that it says x needs to be less than 15, but not equal to 15. So the way I would write can't be equal to is I write an open circle around the 15 and I start shading towards the left because x can be smaller than that number. However, x also is going to be bigger than negative 17. So I draw an open circle around negative 17 and I start shading there. So what we're saying is that any number between negative 17 and 15 will work. Notice that we didn't extend this beyond 15. So x greater than negative 17, I didn't extend beyond 15. X less than 15, I didn't extend beyond negative 17. I stopped at those cutoff values. And that's how this interacts. If you want, you can test numerical values. You could plug in a value like 0, which is between negative 17 and 15, and see that it works. You could plug in a number like 20, which is above 15, and see if it works or not. You could plug in a number like negative 20, which is below negative 17, and see if it works or not. As interval notation, we would do parentheses, negative 17, comma, 15, and then another parentheses. So that's the solution to this absolute value inequality. We solve it, we get two equations, and we need to figure out how they interact. In this case, the two numbers broke up our number line into three different regions, and the middle region was the one that we were looking for. Let's try another example. Let's look here at example 4, where we have 5 times the absolute value of x plus 3 is greater than or equal to negative 10. And then the other equation is 5 times the absolute value of x plus 3 is less than negative 10. If you want to push pause on this video and try these on your own, then that would be a good thing to do. I will do these in a couple of seconds. Okay, so let's start these. First thing I would do in this first equation is divide both sides by 5. That would give me the absolute value of x plus 3 is greater than or equal to negative 10. Dividing by a positive number doesn't do anything to the sign. So here we have a non-negative or a positive number on the left. And it's stating that that needs to be greater than or equal to negative 10. Well, that is always true. So for this absolute value inequality, it's always going to be true no matter what you plug in. And therefore, the solution to this is all real numbers. Any real number you plug in for x will make this equation true. In the other equation, Oh, and if you wanted to do that in interval notation of all real numbers is parentheses, negative infinity, comma, positive infinity, and then in the parentheses. For the number line, you just draw a line forever to the right and forever to the left. I don't need to draw that out. In this second equation, dividing by 5 would give you that the absolute value. Oh, I misspoke here. This should be -2. So when I divide by 5 on both sides, I get absolute values in the first equation is greater than or equal to -2. A non-negative is greater than or equal to -2. That's always true. Therefore, all real numbers. Excuse me. Same thing here. When I divide by 5 on both sides, I get absolute value of x plus 3 is less than -2. And again, what we're saying is that a non-negative number is going to be less than -2. That cannot happen. All positive numbers are going to be bigger than -2. 0 is bigger than -2. So that can't happen. And therefore, since that's always false, we get the no solution case. So the answer to this second equation is no solution. Notice in both of these, basically when we isolated the absolute value, we got our inequality compared to a negative number. In one case, that was always true, so my solution was all real numbers. In another case, that was always false, so I had no solution. And as far as writing this in set notation, the no solution in set notation is the empty set. And symbolically, it's this symbol. You put a 0 with a slash through it to mean the empty set. Also, you could have done all real numbers as well, and with symbols as that capital R with double slashes. So either way, empty set is no solution. Capital R with double slashes means all real numbers. So there we go. Again, I made a mistake on that very first one. When I divided by 5, I should have gotten a -2, just like I have up here now. Let's go ahead and try the inequalities in example 5. If you want, you can solve these on your own. Push pause on the video. In a couple of seconds, I will go over both of these inequalities. In this first one, what we would do is we would subtract 5 from both sides, isolating the absolute value. That would give me the absolute value of x plus 3 is less than 1. Then I would create two inequalities. Since I have a positive number on the right-hand side, I can create two inequalities. One that says x plus 3 is less than 1, and the other, where I use the negative, becomes x plus 3 is greater than -1. Again, I have to flip the sign when I use the negative because that's like multiplying both sides by a negative number. Now I can subtract 3 from both sides. We end up with x is less than -2, or x, well, when I subtract 3, I get greater than -4. This or may be confusing to you. Some people would maybe write the word and instead of or, because the way these interact on the number line can kind of be a little bit tricky. I tend to like or because we get the two options, but other people may want to write the letter and, or the not letter, the word and. So in any case, we have a -4 and a -2. Neither are equal. Whoops. So we're going to draw an open circle around each. And then x needs to be less than -2, along with x being greater than -4. So notice what area I get. I get the area of this middle region here between -2 and -4. In terms of interval notation, the interval notation here is pretty straightforward. We're going parentheses, -4, comma, -2, end parentheses. So that's the solution to this absolute value inequality. Let's look at the next one. In this one, to isolate the absolute value, the first thing I would do is subtract 4 from both sides. So that would give me -2 times the absolute value of x minus 1 is less than or equal to -12. Again, -8 minus 4 gives me a -12. Then I would divide by a -2. Now be careful, when you multiply or divide both sides by a negative, the sign has to flip. So we get absolute value of x minus 1 is greater than or equal to a +6. Again, I had to flip the sign because I divided both sides by -2. Now I can separate this into two equations. X minus 1 could be greater than or equal to 6, or x minus 1 could be less than or equal to -6. Adding 1 to both sides gives me that x is greater than or equal to 7, or x is less than or equal to -5. And then I kind of think through how these two things interact. I usually draw this on a number line. Some people don't do that, but I usually do. So 7 is to the right of -5. Both of these have equality. So when I draw a circle around the 7, I will fill it in, make that a solid circle. Same thing with the -5. When I draw a circle around that, I'll fill it in, make that a solid circle. Oop, that wasn't very good. Okay, we get the idea. Now, x being greater than or equal to 7 means numbers in this right-hand region will work. X being less than or equal to -5 means the numbers in this left-hand region will work. And the middle region is the region that's not going to work. As far as interval notation goes, we'd go from parentheses, negative infinity, comma, -5, so up to -5, and then do a closed bracket because we could equal -5, and then union that with closed bracket 7, comma, positive infinity, parentheses on infinity side. So that would be the interval notation for this example. And that's how we solve these inequalities. Notice that in the last one, we just had the middle section. In this one, we have sort of the two end sections. With equations like this, where I have a single variable and that single variable is inside my absolute values, then those are the two types of solutions we can get outside of the all real numbers or no solution types. We've seen a lot of different inequalities with absolute values, all of them having this variable inside the absolute value and no variables outside the absolute value. Like I said, that's not the only type of absolute value inequality or absolute value equation we could run across, but that's the only type that we're going to deal with right now in this section. Now, the thing about solving all of those absolute value equations is that this prepares us to find x-intercepts, and I guess y-intercepts as well, when we deal with absolute value functions. So we've seen some absolute value functions and how they've been transformed or translated from our base absolute value function. We looked at that in a previous section. And now we want to look at some features of that absolute value function. A couple of the main features we look at are the x and y intercepts. An x-intercept is a point which is on the graph and also falls on the x-axis. Because it falls on the x-axis, it's going to always have form x comma 0. And with any function, you could have 0 x-intercepts, 1 x-intercept, or multiple x-intercepts. It turns out with the absolute value function, you could have 0, 1, or 2 at most. A y-intercept is a point which is on the graph and also on the y-axis. So it's going to have form 0, comma y. And any function could either have 1 y-intercept or 0 y-intercepts. With absolute value functions, the ones that we're looking at anyways, they will always have 1 y-intercept. So absolute value functions can have 0, 1, or 2 x-intercepts. Absolute value functions will have 1 y-intercept. Again, the absolute value functions that we're looking at. Now, in order to expand the vocabulary here, an x-intercept we know is a point on the graph and has the form x comma 0. So it's on the x-axis and on the graph as well, has the form x comma 0. Another way we can phrase finding this x value is we can phrase it as we want to find a 0 of the function. We say that an x value is a 0 of the function if when you plug in that value, you get an output which is 0. So it's a 0 of the function if you plug it in and you get out a 0. Notice that plugging in an x and getting out a 0 is going to force us to have a point x comma 0 that satisfies the function. So every 0 of a function is an x-intercept. I should say, let me rephrase that. Every real number that I plug in, which is a 0, is going to be an x-intercept of a function. So zeros and x-intercepts are kind of interchangeable. X-intercepts are the actual points. Zeros are the x values. Now, I've said a lot about x and y intercepts, but because a y-intercept has the form 0 comma y, in order to find the y-intercept, all I have to do is plug in 0 for x and then solve the equation for y. And in a similar move, if I want to find the x-intercepts, I just need to plug in 0 for the y, so 0 for the output, and then solve for x. This is the same as finding the zeros of the function. Those x values will be zeros, and then the x comma 0 becomes the x-intercept. So to find y-intercepts, we plug in 0 for x. To find x-intercepts, we plug in 0 for y. And when we do this, find x-intercepts, when we plug in 0 for y, we're basically going to be solving an absolute value equation, just like we saw earlier. X and y intercepts are key features of the graph of these absolute value functions. And most of the time when we graph the absolute value functions, we use transformations. But you can also plot points and those key points like the x and y intercepts along with the vertex for reference as well. So if I had to graph by hand, I can use transformations like we saw in a previous section, and we can use some key points like the x and y intercepts along with the vertex. Again, the vertex of an absolute value function is the bottom point of the V. And on our base absolute value function, the origin is the vertex. So the origin is the vertex of our base absolute value function. Obviously, when that gets shifted up, down, left, and right, then that can move around. So let's do an example where we find the x and y intercepts of the following function, and then we might find the vertex as well, and then we'll graph that function based on the x-intercepts, the y-intercept, and the vertex. And then we might also just graph it using technology too. So let's start out by finding the x and y intercepts. Now, here we have f of x is equal to the absolute value of x minus 3 minus 5. To find the y-intercept, we're going to plug in a 0 for x. So we plug in x equals 0. In other words, I just plug in 0 into my function and I find the output. That output is going to be a y value. So we're getting, in this case, absolute value of 0 minus 3 minus 5, which is the absolute value of negative 3 minus 5, which absolute value of -3 becomes a +3. +3 minus 5 gives you a -2. So that means when I plug in 0, I get out a -2. So the y-intercept is going to be the point 0, comma, -2. That's a point that passes through the function because I know it does, because it satisfies the equation. So it's on the graph of the function, and it's also on the y-axis because it has the form 0, comma, -2. Now there's only going to be one y-intercept because if you had two different y-intercepts, it would violate the ability for this to be a function. It would fail the vertical line test. So we only have one y-intercept, and it is 0, comma, -2. On the other hand, to find the x-intercepts, what I would do is I'd plug in 0 for my y value. My function output is, in fact, my y value. So I can replace that f of x with just the letter y if I want, but usually I just leave it as f of x. I know that my output is my y value. So I'm saying that this output has to be equal to 0. You can either write 0 is equal to the absolute value of x minus 3 minus 5, or you can reverse that order and say the absolute value of x minus 3 minus 5 is equal to 0. It doesn't really matter which one you use, you just have to solve for x in either case. I think I'll use this one because in the previous cases, we've always had our absolute value on the left-hand side, so I'll use it in the second. I'll use the second form. To solve, what we would do is we'd add 5 to both sides. That would give absolute value of x minus 3 is equal to a +5. Now I have two different equations. Either x minus 3 is equal to +5 or x minus 3 is equal to a -5. Solving each of these, I'd have to add 3 to both sides. That would give me x is equal to 8 or x is equal to -2. So what I have here is, first off, the way I found the x-intercept is I plugged in 0 for y. My output has to be 0. And I found two values that if I plug them in, give me a 0. So these two values of 8 and -2 are the zeros of this function. That means the x-intercepts, well, that means I'm going to have two x-intercepts, one which is at the point 8, comma 0, and the other at the point -2, comma 0. So I have two x-intercepts right there. Now, by the way, just based off of the transformations that we saw earlier, our vertex of our base absolute value function is at the origin. This has been shifted from our base function right 3 units and down 5. So technically, our new vertex is going to be at the point 3, comma, -5. Let's go ahead and graph all of those points, both the vertex, the y-intercepts, and the y-intercept singular, and the two x-intercepts, and see if that all lines up to what we get with technology when we graph this. All right, so here we go. We said we had a y-intercept at -2, 0. Oh, I'm sorry, I misspoke. 0, -2. -2, 0. So my y-intercept is right here at 0, -2. I had an x-intercept at -2, 0. That's what I was thinking. And I had an x-intercept at 8, 0. And then I also said that the vertex is at 3, -5 right here. Notice that what I'm getting is I'm getting a graph. We know what the absolute value looks like. It looks like a V. I'm getting a graph that's moving up to the right this way, starting at my vertex of 3, -5, and also moving up and to the left, going through this way. Going through both 0, -2, my y-intercept, and -2, 0, which is my other x-intercept. Again, I didn't draw this very perfectly, but that's the kind of graph that you would get if we had to draw it by hand. You can confirm that using technology. Here I already typed it in, so if I click that on, you can see the graph is exactly what we were looking at. So we can see that we get exactly the graph that was described. And oftentimes with technology, you can actually highlight and hover your cursor over a point, and you can see the x-intercepts at -2, 0 and at 8, 0. You can see the y-intercept at 0, -2. You can see your vertex here is at 3, -5. That is how we can use those x-intercepts and the y-intercept and the vertex to graph a function, graph an absolute value function. And again, you can also just graph it using some technology too. I obviously use Desmos, but you can use the TI-84 if you want to use that as well. Let's look at this function and do the same thing. Let's find the x-intercepts and the y-intercept of this function, and then we'll graph the function. In this case, I'll graph it using technology. I won't draw all the points. I'll just show the graph of it using technology. If you want to find the x-intercepts and y-intercepts on your own, push pause on the video. All right, so to find the y-intercept, we simply plug in 0 into the function and we find the corresponding output with input of 0. So we plug in 0 for x and then we find the y value, which is the output. So 2 times the absolute value of 0 minus 8 plus 10. Well, that's going to be 2 times the absolute value of -8 plus 10. Absolute value of -8 is going to be a +8 times 2 is 16. When I add 10 to that, I get 26. So that means my y-intercept is the point 0, 26. In order to find an x-intercept, I'd plug in 0 for y. And just like last time, what we're going to do is we're going to say the output is 2 times the quantity absolute value of x minus 8 plus 10. And then I'm going to set that equal to 0. I'll put equal to 0 on the right-hand side. But again, if you want to write equal to 0 on the left-hand side, you could do that as well. Then we solve this. The first thing I would do is I would subtract 10 from both sides. And then I would divide by 2. That gives me absolute value of x minus 8 is equal to a negative 5. Just like before, we can see that this is a non-negative equal to a negative number, which is never going to be true. So this is always false. Therefore, there is no solution to this absolute value equation. And if there's no solution to this absolute value equation, that means that there are no x-intercepts around. There's no zeros either. There's no x values, which when you input them, give you out a 0. So no solution to the equation means that there are no x-intercepts. So there we go. That's it. By the way, if you look at this, the vertex is going to be at point 8, 10. So if you're actually going to graph this by hand, it's at 8, 10. And you can see that there's a vertical stretch of 2 going on as well. So you'd shift it right 8 units, vertically stretch it by 2, and then shift it up 10 to get the h of x from your base absolute value function. Let's go ahead and graph that. Like I said earlier, I'm just going to utilize technology to graph this. We have 2 times absolute value of x minus 8 plus 10. So we knew our vertex was at 8, 10, and then it was going to go up by a vertical stretch of 2, so a little bit steeper than usual. And we get this. Again, vertex here is at 8, 10. And if I scroll over, we can see that it does hit the y-axis at the point 0, 26, just like we said. So those were our 2 influential points. And because the vertex is at 8, 10 and the absolute value function is pointing up, there's no way you can cross the x-axis. That's why algebraically we got no x-intercepts, because it never goes below that point 8, 10, so we can never cross over the x-axis. That's different from f of x, which obviously crossed over the x-axis at 2 different places. Now, the last example has a slight change in terminology. We're going to use the terminology of zeros instead of the terminology of x-intercepts. And we're going to be asked to find the zeros and the y-intercept of the following absolute value function. G of x is equal to 3 times 2x minus 1 in absolute values minus 6. If you want to, push pause on the video and then solve this on your own. Otherwise, in a couple of seconds, I will show you how it's done. For the y-intercept, we do the same thing as always. We plug in an x value of 0 and then find the y value output. So g of 0 becomes 3 times the absolute value of 2 times 0 minus 1, and then minus 6. When I simplify the inside, that becomes 3 times the absolute value of -1 minus 6, which is 3 times 1 minus 6, which gives you out a -3. So the y-intercept is the point 0, -3. To find the x-intercept, or technically this is going to have multiple, so we're going to have x-intercepts, we plug in the y value or the output value as 0. Again, I like to put 0 on the right-hand side, so I'm going to write 3 times the absolute value of quantity 2x minus 1, and then minus 6 is equal to 0. Adding 6 to both sides gives me 3 times the quantity 2x minus 1 inside of an absolute value is equal to positive 6. Then I would divide both sides by 3. I'd get absolute value of 2x minus 1 is equal to 2. And now we're going to have two equations that are going to stem off of this single absolute value equation. We get that 2x minus 1 is going to be equal, could be equal to 2, or we get that 2x minus 1 could be equal to -2. Adding 1 to both sides, we get 2x equals 3, or 2x is equal to -1. I'll write my answers in decimals, but the zeros here are that x could be equal to 1.5, that's 3 divided by 2, or x could be equal to -1/2 or -0.5. Linguistically, we say x could be this or x could be that. Another way we can say it is that the zeros are x equals 1.5 and x equals -0.5. I'm not picky on the language. I just want you to know that there's two of them. They both give out a 0 when you plug them in for your input value in g of x. And if there was a question that asked you for the x-intercepts specifically, then you would say those happen at points 1.5 comma 0 and at point -0.5 comma 0. So there we go. That's how we find the x-intercepts and the y-intercept. And that's the main issue that we're looking at. Now, the secondary issue that we usually find, or the secondary point, some people would say this is the primary one when you graph, is the vertex. Now, in terms of the vertex, this is kind of hard to see sometimes where the vertex should be if there's a lot of horizontal stretching or horizontal shifting going on. It turns out in this case, the vertex is at the point 0.5, comma, -6. The reason it's not at 1, -6 is because this vertical stretch of 2 times x minus 1, technically this horizontally stretches by 2 before we shift over 1 unit. And that's throwing things off. So a lot of times when you see this, if you want to look at it through a shift lens, well, I'd have to factor out a 2, and I get 2 times the quantity x minus 0.5 and then -6. So that's a right-hand shift of 0.5 and a shift to the right of 0.5 and a shift down of 6. So that's why the vertex looks the way it does. Again, on this section, the important parts were finding the y-intercepts, the y-intercept singular, and finding the x-intercepts, in this case, plural. Let's go ahead and graph this equation and see what it looks like, just to confirm that we got the correct x-intercepts and y-intercept. Here I've graphed this absolute value equation or the absolute value function into Desmos. And you can see that the vertex is at 0.5 comma -6, just like I said. You can see that the x-intercept, one of them is at 1.5 comma 0. The other x-intercept is at -0.5 comma 0. And that the y-intercept is at 0, -3. So all 4 of those points show you where the absolute value function is going to lie. Hopefully that makes sense. Now, obviously, I've graphed this in Desmos. You can also graph this on a TI-84 calculator. There'll be a companion video on how to graph with the TI-84 calculator. Again, we have done a lot of other work with this absolute value function using transformations. So hopefully you're fairly comfortable using this absolute value function, not just this base absolute value function, but all kinds of transformations of that. Remember that when you're solving, the reason we're getting 2 answers is because this absolute value operation basically does 2 things. If x is non-negative, then it gives you back the x itself. If x is negative, then it gives you back the opposite of x. So it's kind of like if this absolute value operation is like a piecewise defined operation. If x is in this range, you do this. If x is in this other range, you do this. So that is it for what we're going to cover in this section on absolute value functions. Again, things can get much more complex. We may see some of that complexity later, but that will be for a future video.